Hi, I am Dheeraj. I'm, I'm from University of California, Santa Barbara. This is a joint work with my advisor, Professor Yushanga. In this paper, we are looking at controlling the dynamic regret of a linear quadratic regulator system. Formally, we define the problem statement as follows. So, the we model the game as a game that continues for n rounds, where at each round the learner is at some particular state xt and the learning agent plays a control signal ut. Now, based on the current state and the control signal, the system transitions to the next state according to this linear law plus some perturbation term wt. Here, the wt perturbation is chosen adversarially, and we assume that the norm of the perturbation is bounded by 1. Then the agent suffers a loss, which is a quadratic loss that is given by this expression. So we assume that the matrices A, B, Rx, Ru are all known ahead of time. Next, we define a class of benchmark policies, namely disturbance action policies. So they are defined as displayed in this equation, where K infinity is the optimal state feedback controller arising from the recorded recursion, and QM is basically defined as this, which is doing a weighted uh, linear combination of the past M disturbances. So here capital M is a matrix, and small m is basically saying that we have a sequence of matrices, and the sequence length is smaller. We assume that this matrix sequences belongs to this set scripted M as defined here. So basically, as we the operator norm of the matrices in this sequence reduces at an exponential rate. The performance of the learner is measured in terms of the dynamic policy regret, which is displayed in this equation. So here, each MT in this expression is the comparator DAP policy at time step t. So we compare against a sequence of DAP policies, and each DAP policy is identified by some matrix sequence M. Next, let us motivate why we should consider such a notion of dynamic regret. So, in order to motivate this, for simplicity, let us assume a univariate setting where the state, perturbations, control signal, everything is in 1D. Let us divide the time into 3 sections. So the entire time horizon is divided into 3 different sections. In the first section, the perturbation looks like some sort of a stochastic process. In the second section, the perturbation might actually have a piecewise constant structure. And in the third section, again, the perturbation might follow some form of a stochastic process. So if you look at the DAP policy, its decision is basically based on average of first sequence of observations, right? So in this first section, it is possible that the best policy might have to do an averaging of a first cup of observation, where the window size for the average might depend upon the characteristics of the stochastic process generating the perturbation in this first section. On the other hand, in the second section, in order to counteract the disturbance, a good policy might only need to know what is the disturbance in the previous time step, because from the bulk of the time in the second section, the disturbance is perfectly predictable. So if you know what is the disturbance in previous section, it is possible that that is exactly the same disturbance in the next section except for this change point. And because of this, we can easily counteract the disturbance by just looking at what is the value of the disturbance in the past time step. In other words, a good policy in the section number 2 only need to do an averaging with the window size of 1. And similarly, in the third section, a good policy might have to do an averaging with a window size much greater than 1. And the window size is dictated by the properties of the stochastic process that governs the perturbations in the third section. So overall, we observe that the best policy at different time steps can actually be different. The best DAP policy in different time steps can actually be different. And hence it is not very good in order to compare our performance against one fixed policy. So we use this notion of dynamic regret in order to compare the performance of the learning agent against the performance of a sequence of DAP policies chosen in hindsight. Now let us try to understand how we incorporate safety constraints. So consider an example of controlling a drone. Depending upon the current state and the battery level, we can only apply a range of allowable torque values. So if you exceed some allowable range of torque values, it might actually burn the motors or even drain the battery very quickly. So in this paper, we model a set at any particular state xt, we model a set of safe control signals by this decision set ft here. So ft is basically the set of all control signals which can be produced by one DAP policy in this class scripted at this particular state xt. Basically, it contains control signals that are produced by the DAP policies in this class scripted at that particular state xt. Now, by appropriately setting these parameters of the benchmark class, basically small m, capital R, and gamma, we can control the magnitude of the control signal Vt. To ensure safety, at each round, the learning agent plays a control signal from this feasibility set Ft. So this is how we ensure safety in the LQR problem that we study now. And this is an instance of proper learning where the learning agent how to choose its decision from a given feasibility set. There is a prior work by Foster and Simkowitz that provides a reduction from the LQR problem to online linear regression problem. Specifically, the results of Foster and Simkowitz imply that the dynamic regret in our setting can actually be bounded by the term displayed here in the right hand side. So here this function at cap, which takes in a matrix sequence as input and produces a loss function for that particular matrix sequence, and its expression is as displayed here. So remember that QM from this definition 1, it is basically a linear map of the matrix sequence. So this function, this loss function at cap is basically a linear regression loss acting on the matrix sequence M. And it is known that in a bounded domain, linear regression losses are X to concave. So this result implies that if we have an online linear regression algorithm which can control the dynamic regret at the same time making the decisions MT-alg inside this feasibility set scripted M, then we will be able to control the dynamic regret of the LQR program. So we can look at literature about existence of such algorithms which simultaneously guarantee good dynamic regret under linear regression or exponential losses and at the same time ensure proper learning, where the decisions of the learner will have to obey the feasibility constraint. Unfortunately, there are no such algorithm to date that is available which satisfies both of these properties. However, there is a very closely related algorithm that is given in this paper by Baby and Wang 2022, which basically minimizes the dynamic regret under exp concave losses, with one drawback that they can only support decision sets which are L infinity bounded board. So basically box constrained decision sets. But in our case, the decision set is given by the scripted amp here, which is definitely not a box constrained decision set. So we cannot apply the results of the paper of Baby and Wang 2022 directly to control the dynamic regret of the LQR problem while ensuring this safety constraint. So the central question that we ask in this paper is how can we extend their algorithm in order to ensure proper learning, specifically for the problem of proper online linear regression. To answer this question, we provide a very generic algorithm that can work for any online linear regression setting. So in online linear regression setting, we are given at each round T some covariate matrix AT. Okay. And this covariate matrix AT and a bias vector BT defines the linear regression loss FT of W, which is also displayed here. So what we propose in this ProDR.control algorithm is basically a black box reduction that can take the algorithm of Baby and Wang 2022, which only works for box constraint decision sets and exp concave losses, and transform that into an algorithm that can work for any customer, any input provided decision set D. Okay. So let us see how that is accomplished. So here in this algorithm box, the scripted A is basically the algorithm from this algorithm that actually works for exp concave losses and a box constraint decision set. So at each round T, we will actually receive a decision WT from this box constraint algorithm scripted A. Now, note that this decision WT may not actually lie in the decision set D, okay, which is the decision set of our interest. So in order to make it lie inside the decision set D, we project the output WT to this decision set D by using a min-max rule. This was defined here in line 3. Then we construct a surrogate loss LT of W, which is defined as this, where G is related to the Lipschitz constant of the loss function FT of W. Where the Lipschitz constant is calculated according to the Lipschitz constant is calculated across the tightest L infinity box that encloses the decision set D. Okay. And then once we construct the surrogate loss LT of W, we pass that surrogate loss to the box constraint algorithm scripted. This is how we actually perform this reduction. So the main idea here is that if you consider any comparator W that belongs to the decision set D, we can easily see that LT of W will be exactly equal to FT of W whenever W belongs to D, because ST of W will be 0 if W belongs to D. Now, using Lipschitz type argument, we can show that Ft of Wt cap is less than or equal to Lt of Wt. That actually follows from the Lipschitz. So basically what we have shown is that the per instance regret with respect to the losses with respect to the linear regression losses, ft is bounded by the per instantaneous regret with respect to the losses lt, uh, and box decision set that encloses the actual decision set d. So since we already again we also show that this losses lt of w remain exp concave over a box that encloses the true decision set d. So in order to control, so if we can control the regret with respect to the surrogate losses lt of w and the decision set which is a box, we can definitely control the uh, dynamic regret with respect to the losses ft of w and the decision set d. So and we know that by choosing a scripted A as the algorithm of Fabian Wang, we can optimally control the dynamic regret with respect to the losses LQ of W, which we prove to be exponential. Yeah. So that's how we actually accomplish this reduction. And when applied to the LQR setting, it can be shown that this particular PRODR dot control algorithm can be instantiated in order to provide a dynamic regret like this, where TV is the total variation incurred by the sequence of DAP policies in hindsight. Oh, and one more thing is that the design of the algorithm PRODR dot control is actually inspired by this black box reduction works of Katkowski and Arbono 2018. We also show that this dynamic regret rate is unimprovable in a minimax sense. So these are the details of our paper, and please check out the full paper available in the workshop site for more details. Thank you.